computer. Unlike the MyOpen Math type question where there's that messenger instructor button, I didn't see something like that in Khan Academy. So if you get stuck on something there, you'll have to use one of two things. Either in Canvas, just the inbox to write to me, or you could write to the whole class by putting it in the the learning forum. And so that would be, I would recommend that because you kill two birds with one stone. You get a post in the learning forum for some credit, and then you get someone to answer your question. And I don't think we have any comments in here yet. Okay, nothing in there yet. All right, so paper circle time, which should be back one page. I have another version of this that's a printable version that I've made before. And I don't know if anyone checked out that one. It's almost exactly the same. The formatting is different because I did it in a different program. And I had to kind of try to copy and paste that into Canvas here. So ultimately, there's a bunch of questions in bold that I would like you to write down answers for. So you could either write it down on paper, take a picture, scan it, and upload it, or you could hit the submit button at the top and then type in your answers, whichever you prefer. And let's see. I think we're ready to go. Any questions? Paper circle time. All right. So the theme of this is the things you can make, the shapes you can make out of a paper circle. So I have a larger than usual paper circle that I use for this activity. Usually I just cut it out of an 8.5, 11 by 11 piece of paper. And the first thing kind of question here is, how can you find the center of a paper circle? So I just took a baking dish at home that I use for cakes, and I just traced it on top of this piece of paper, and I have no idea where the center is. I mean, it's somewhere in the middle, but my baking dish didn't have a mark that said, hey, here's the middle. So the first thing is we're just going to play around with finding the center. So the first step, let me pull this up again, is using the circle cut out of paper, just fold the circle in half and crease it. So I'm going to come up over here to my wall, and I'm going to carefully fold my circle in half. And for this activity, the better your cutout was, the better this works. But if it's not perfect, oh well, we'll get by. So fold that in half, make the crease, right? And usually I ask, what shape is this? So if I was in an elementary school right now, I'd ask them to tell me, hey, what is this sucker? And they would all give me lots of answers. Almost nobody, and depending on the grade, like maybe if I did this in 3rd grade, very few would say semicircle. They would say it's half a circle, which is good enough, right? So then the first question that does a little fraction stuff is, how much of the area of the circle is in the semicircle, right? So nice, easy fraction to work with, and pretty young kids will get that no problem. So that's not one I need to write down an answer for. So then we open it up again, and when you open it up, you can see there's this line running through it. Does anybody know what that line is called?
The diameter?
Yeah, that's the diameter of a circle. So we open up the circle again, and then we're going to fold to make a new semicircle. So I'm on this step right here. So I'm just going to fold it in a different spot. And I'm going to make another crease in it. So I have a new crease. And, oh, that's interesting. I don't know if you can kind of see that. My new crease and my old, whoa, my screen just went crazy on me. My new screen and my old my new crease and my old crease meet. So the question is, what do you see about the fold for the second semicircle? Well, one thing I see is that it meets the fold for the first semicircle, okay? What do you think is going to happen when we fold a third semicircle?
It's going to intercross with both of them.
It's going to cross both of them in the same spot, right? So let's do that. Let's make a new fold. And all I'm worried about here is folding it in half. I'm not really worried about the other creases at the moment. I'm just curious. And I think I did a pretty good job cutting out my circle because they wow, they meet pretty good in the middle, and you can kind of see the shadows of my creases there. They meet pretty good. So one thing I'm going to do right away is I'm going to put a dot where they meet so I can remember where my center is. Now I can see it in the creases, but I'm going to just emphasize it anyway. So I just made a little dot there in the middle. Now I have a green screen in the background, so when I get too close to the camera, weird stuff happens. My apologies for that. All right, so we're getting through this. All right, can you see why? So sometimes I answer the question for you after, and this is one of those cases. So anytime I star something, it's an important definition. All folds intersect at the center when I make a semicircle. So any fold that passes through the center of the circle forms a diameter. So a diameter is any line that passes through a circle that hits the center. Right? And that's one way to define a diameter of a circle. So again, we open it up, we put the small dot. Now here's where things start to get interesting with the folds. This step right here is where I'm at. So we want to fold the edge of the circle to the center and crease. Okay? So I have my center right there, and I am going to fold, I'm going to bring that top down till it just perfectly touches the center, and I'm going to hold it there and come back up and crease across. So my crease, can you see, just barely touches the center. How are we doing there? I'm going to open it up for a sec. I have a new line coming through my circle there. It's not a diameter because it doesn't pass the center. Any line that cuts through a circle is called a chord. If that chord happens to hit the center, then that chord is also a diameter. So this is just a chord in a circle. That's C-H-O-R-D, chord. All right, and I have a definition for that because it's on this starred line underneath. All right, so here's where things get a wee bit trickier. We want to make a second fold. Oh, I'm confused here. You guys see me and I'm touching my screen like you guys can see it. Let's see, is there a way I can split my screen so you can see me and that? I'm going to try something. Share. Okay, so you should now see my canvas screen. Can I make it show me too? Is there any chance that you see the video of me in my fake classroom sitting on top of canvas? Oh wait, isn't that part of the view in your screens? Can't you see the picture of me and the screen when you have Canvas, Zoom open?
Yes.
Okay, sorry, I'm kind of new at Zoom. All right, can you make the picture of me a little larger, or is it just stuck at one size? And I guess
in the top right corner, it says it has the option to swap the shared screen with the video. So it makes you larger, and then the shared screen, it makes it almost impossible to read.
Okay.
But then you're the larger picture.
But you could switch back and forth there. Yeah, so I guess what I need is sometimes I need you to see me, and sometimes we need to see the directions. Okay, we're just gonna, so if I do something and you get lost in what I'm doing, just shout out and I'll try to make it more clear. If you lost track of the directions, or maybe you flew through them without me, that's okay too. I'm at the stage where I'm trying to make a second fold to the center.
You can also do side by side.
You can do a side by side?
Yeah, but you'll be slightly smaller. Okay.
Yes, and I guess it depends on what kind of device you're on. I don't know if you can do that on an iPad. And an iPhone would be, or some kind of phone would be out of the question. All right, so we'll get through this. So put your paper back so that your chord, your first chord, has a fold. Okay. So I don't know if you can see me right now, but I have my first one folded. And then what I'm going to try and do is I'm going to just rotate it a little and take top of the, some part of the circle away from that fold. I'm going to try and get it down to the center, but I'm also going to angle where it hits to match exactly at the other. I want a perfect point where the new chord and the old chord are going to meet, and I want the edge of the circle to touch the center. Okay, so I'm going to have to go up to my wall to make that happen. I'm going to switch views for a sec. Stop sharing. No, wrong button. Stop sharing. There we go. All right, so I'm going to try and fold that down while getting the edge of it to match the edge of the other chord. And that takes a little finessing to make that happen. I think I got it right there. And once I think the edge lines up on the center and I get a nice sharp tip where they meet, but then I'm going to crease across to the best of my ability. And so what I should get is this ice cream type shape, ice cream cone type shape, and I should still barely see the point, the center point, right where those two folds meet, is what I'm going to try and do there. And sometimes this takes me a couple of folds to get it right. Some days I get it right, but I have a nice sharp point at the bottom there, as sharp as I can get it, where both chord folds meet at the center. All right, so then the next direction is to repeat that one more time. So we're going to take this last arc of the circle here, and we're going to fold it down, and three things should happen if I do this well. The edge of the circle should touch the center, and then both edges of the chord should meet the other two chords. So if your circle is cut out well and your folds are good, that should work perfectly. If not, there's going to be a little bit of wiggle room one way or the other. So I try to fold that tip down and just perfectly meet the other chord. So I'm going to get one chord to meet, and then I'm just going to kind of gently work it down on the other side and hope I get two sharp points. And I'm close, but not exact today. All right. So once I've done that, I can still just barely see the center there. And again, depending on your cutout and how sharp your edges are, or maybe you have a little gap on the top edge, that's okay too. You should get a shape that looks like this right here. And it should be pretty symmetric, meaning if you change the order of the folds, it shouldn't look much different.
So this is kind of like a Celtic knot?
Yes, 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 yes. It's like a Celtic knot. Cool. Yep. Yeah, we have those overlapping arcs, which is kind of neat. So, like if I flip it over and I try to ignore the arcs, what shape do you think we made right here? What shape do you think you have in your hand?
Triangle.
Okay, it's a triangle. So I'm going to whip out my notebook because I wanted to start taking some notes here. Oh, shit. No. What did I just do? Don't push that button, Gary. Oh, share. There we go. And share. Yeah, it's a triangle. Is it, can we give it another name? Does it have a better name than just a triangle? Something slightly more specific.
Equilateral.
Yeah, it turns out it's equilateral. And an equilateral triangle is pretty darn special for a few reasons. Okay, so the stuff we're going over here is at the end of section 10.1. So this is like the third stage of section 10.1. 10.1 is called plane figures. And of the plane figures, it goes over points and lines and what a plane is. And the type of plane figure we're jumping into now in general is called a polygon. Polygon. And poly means many and gon means edges. So polygon translates as, actually it's really many angles, but I'm going to call it many edges. I guess this should be true to what gon means, many angles. It also has many edges. The simplest polygon that you can make is a three-sided polygon. And I use the word side a lot, but that's like calling a decimal 0.5 versus 5/10. Sides are actually called edges, is the technical term for them. Sides kind of a slang thing. And a three-sided polygon is a triangle. Three-edged, sorry. We have a special kind of triangle here called an equilateral triangle. And this triangle, this equilateral triangle, has another special property. Can anybody else tell me something else special about the triangle we made? Let's see, where'd you guys go? I lost you. There you are.
All of the angles are less than 90 degrees.
Ooh, yeah. Okay, so all the angles are less than 90 degrees. And as far as angles go, this particular triangle has what's called acute angles. So this equilateral triangle has acute angles. And acute angles means that they're less than 90 degrees, which is a right angle, or sometimes that's called a square angle. Okay. Anything else you notice about those angles besides they're less than 90 degrees? Yes, exactly. All of the angles are the same length. So I just got a couple of chats about this too. Thank you. So for this, it's also equiangular. So this is equiangular. And if a polygon happens to be equilateral and equiangular, if both of those conditions are met, then we give it another name, and that's called regular. So this is a regular polygon. And regular, again, means equilateral and equiangular. Okay, so we've got an equilateral triangle which happens to be equiangular, which makes it a regular polygon, or a regular triangle, to be more specific. All right, cool. Let's see where we are on this document. All right, so we made a third chord where the other ones meet. We named this thing. And then I tell you what the answer to that question is above. Okay, next. With the equilateral triangle, find the midpoint of a chord by folding a side so the adjacent vertices meet. So a little more terminology. Page. So I'm going to use just a triangle, but for any polygon, we have a couple of things to consider here. We have these points here. And another word for point when we're talking about a polygon is a vertex. And a vertex is where two edges meet. So this thing over here that we also call a side is more technically called an edge. And the thing about a vertex is here I can have just a point floating in space. It's just a point. It is not a vertex because it's not related to edges. So the only time we call a point a vertex is if it's related to two connecting edges. So for our triangle, what we want to do is we want to fold one of these vertices on top of the other one and then make a little crease to mark the middle of a side. So let's make that happen. And then back to the directions. Let's see, did I switch my views here? I did not. I'm going to switch my view for a sec, make sure we're doing the same thing. So I bring one tip over to the other, and I don't need to fold it all the way in half. All I really need is a little tiny crease right where they meet. So I didn't do a complete fold in half. I just got the very edge there. And then I just want to make a little mark there. It doesn't matter what side you mark it on. Once we make that little mark for the middle, can you see my tiny little mark there? I want to fold the opposite vertex down so it just touches that mark. And I need a flat surface to do this on. So I get the tip to just touch that point, hold it there, and then come back up and crease across. And I accidentally chose some, I didn't accidentally choose it. I chose some paper that's on the edge of watercolor paper, and it's kind of thick. I wish I used the other thin paper I had. All right, so I have a new shape here. Anybody want to guess what the name of this shape is? So hopefully yours looks like mine. And if that fold went well, what you should notice is this short top edge here should be parallel to this longer bottom edge. And so that's a hint to the name of this figure. It has a pair of parallel sides, this one and this one. Could hold it that way too. What is this? Let's see. Yes, it is a trapezoid. And actually, this trapezoid has a specialer name. So let's put that down. Share screen again. I guess I'm going to have to switch back and forth here to make this work. All right, so new page. So this shape actually has many names, so I'm going to go through its names and get to the best one. So once you jump up from a three-sided polygon, if you go to a four-sided polygon, and I'm using slang again, my apologies. That more specifically is called a quadrilateral. Quadrilateral. So quad is I think, is it Greek or Latin for four? So quadrilateral, four sides is what lateral means. And there are special kinds of quadrilaterals. And so one type of quadrilateral is called a parallelogram. Oops, no, I wasn't ready for parallelogram. I lied. Scratch that. Trapezoid next. Trapezoid, which is the one we're on now, trapezoid. And a trapezoid is a quadrilateral, has four sides, with, and there's varying definitions depending on the book you look it up in. My version of the definition is at least one pair of parallel edges. Okay. And so this figure here definitely has at least one pair. It's got one pair. One satisfies at least one. All right, now this is specialer though, because it has another property we're not naming with this description. So let's go back to my picture here. So this has another special property in that these two angles, because they came from that triangle, are congruent. Congruent means equal with geometry. And it turns out these other two at the top are equal also. So because I have these consecutive pairs of equal sides, of equal angles, that gives me these congruent edges too on each side. And so this is called an isosceles trapezoid. And isosceles just means it has a pair of congruent sides, congruent edges. So share, let's write that down. Yes, okay. So this particular one is a special kind of trapezoid. It's an isosceles. I gotta say it that way, otherwise I don't spell it right. Trapezoid. So it's a trapezoid with a, let's see, the right definition here. Yeah, a pair of congruent sides. 95% sure I'm wording that right. Edges, be more precise, Gary. Thank you. Good job. All right. So I have an isosceles triangle and an isosceles trapezoid, which is related to an isosceles triangle. All right, so let's see. What figure is formed? We got the trapezoid, and we get the next step here. Oh, the area of the trapezoid is what part of the equilateral triangle? Oh, that's a tough one. Did anyone figure that one out yet? Question number 7. So question number 6, it's an isosceles trapezoid. Question number 7, the area of the trapezoid is what part of the triangle? So we got the triangle. If we unfold, fold it back down, we have the trapezoid. And if you look at the folds, the answer kind of pops out at you. I'm going to stop sharing for a sec. So I see something here, and when I open it up, it looks different. So this top triangle folds down. Anybody notice anything interesting about what they see right here?
Is it 3/4 of the size?
Nice. Who said that? Monica?
Yeah.
Thank you. Yeah. Notice there are 1, 2, 3 congruent triangles that make up this trapezoid. And when I open it up, I get a 4th congruent triangle. So the big equilateral triangle is actually made up of 4 smaller equilateral triangles. Okay, and I can kind of trace those in here just for fun. So it might help for some of these questions to draw on top of your figure. So I'm going to show you what I'm drawing here. So if I open it back up, can you see my pencil lines? And those pencil lines are trying to show me that there are 4 smaller equilateral triangles that are all congruent that make the big equilateral triangle. So the trapezoid is 3/4 of the original triangle. All right, cool. Next stage of our journey. Share. With the trapezoid, so have your trapezoid in front of you, fold a vertex of the original triangle to its opposite vertex. So just another note from my notebook here, back on this page, and I'm going to draw a crude trapezoid. That's not too bad, Gary. All right, so here's a trapezoid. So I tried to make it so these 2 sides are parallel and these 2 sides are congruent. And so usually when we try to denote parallel sides on a figure, we make an arrow, and the matching arrows are supposed to indicate, oh, those are parallel. And to indicate 2 sides are parallel, we make a slash, or if there's multiple parallel sides, we might have a pair of double slashes. Like if I had a rectangle and I wanted to indicate, I should have used the straight line tool, that these 2 sides are congruent and these 2 sides are congruent. So the single slash here means these 2 match, the double slash here and here means those 2 match in size. And when I talk about vertices, I'm going to do a red. So this vertex and this vertex, these 2 are called adjacent because they're next to each other. Adjacent vertices. And if they're not adjacent, like this one and that one, these 2 would be opposite vertices because they're not adjacent. All right, so on this one, I want to take one of the vertices from the original triangle here and fold it till it touches that one and then make a crease and see what happens. Stop sharing for a sec and attempt to do that. Here's my trapezoid. I'm going to bring this thing over to its opposite edge. And if all goes well and your paper's not too thick like mine, what should happen is these 2 edges should match up nice. And I should get exactly 2 of those congruent smaller equilateral triangles. So this is my new shape. Does anybody know what this new shape is?
Rhombus.
Yes, it is a rhombus. Now, another name for it is a kite, but a kite is a slightly different shape that this just happens to be. And so this shape actually has a bunch of names, but there's a best name. The best name is rhombus. Nailed it. Good job. All right, so some notes on this one here. Over on this page. We left off with trapezoid and isosceles trapezoid. Another branch of the trapezoid family is a parallelogram. Parallelogram. And a parallelogram, you could either say it's a trapezoid with two pairs of parallel sides, or you could say it's a quadrilateral with two pairs of parallel sides. Both lead to the same conclusion. So I'm going to go with the more general definition, but it turns out it doesn't matter. Quadrilateral with two pairs of parallel edges. Parallel edges. So that's a parallelogram. So this shape happens to be a parallelogram because it has two pairs of parallel edges. Now, another thing you might notice about this is all of the sides are the same length. Okay? So that makes this shape an equilateral parallelogram. And so that's one way to define a rhombus. So a special type of parallelogram is a rhombus. And one way to define a rhombus is an equilateral parallelogram. Equilateral parallelogram. And for any of these shapes, there's usually multiple different definitions you can give that all lead to the same conclusion. So one thing I'm wondering about is an alternative. Sorry, I got to move my zoom tools out of the way. Why don't you guys move? Come on. Oh my gosh, why did you do that to me? Move the tools and wrote. And don't let me undo. So I think, and you guys see if you might be able to prove me wrong on this, question mark. Is a rhombus also an equilateral quadrilateral?
Yes.
Quadrilateral. All right. So I am going to whip out a way to investigate that. Last class, I mentioned a program I like called GeoGebra, and I meant to make a link to it. I can't remember if I actually did. And then from the GeoGebra homepage, I like the geometry tool. And I'm going to ask the geometry tool to draw me a line. So I click line and then go click point, click point. So there's some line. And then more, I would like it to make me a parallel line. And the parallel line says select a point and a parallel line. So I'm just going to randomly pick a point out here and then say I want to be parallel to that line. Okay, so there's a pair of parallel lines. So now I'm just going to pick some other random lines. I'm going to go back and pick my random line tool. I'm going to say, let's try this point and that one. Oh shit, is this what I want to do? Maybe this investigation is not going to be where I want. How do I ensure that I have equilateral sides? That means the next one will have to be the same space apart that these two are. Okay, I know how to make that happen. Somewhere here, there's an intersect tool. Where are you? More. Intersect. So I want to know where this one meets and this one meets. All right, so that's one of the vertices of this gon I'm making. If I make that parallel line way out here, I'm not going to have equilateral. So what I want to do is I want to take the distance from here to here and make that same distance out that way. So to make that happen, I guess I need to mark this other point. So bear with me on my experiment. And then I'm going to use the circle tool. So I want to make a circle with a center, a circle with a center. Is this the tool I want? Select the center point, then another point, exactly. So I want to pick this point here and that point right there. So what that does is it says, oh, from F to G is one radius of the circle, and I can find another radius by picking a point where these two meet out here. And we might get to this later in the course, how to build things like this if we do the constructions part of the book, but I don't know if we're going to have time. So I want to know where this circle and that line meet. They meet right there. All right, so my belief then is that if I get my parallel line tool out again, and I say, give me through that point, parallel to that line, that this shape from H to F to G to whatever that point is right there, no, to C. Oh, I happen to hit C. That's fascinating. I got lucky. All right, let's get the polygon tool. So I think this shape right here, if C really is in the right spot, should be a rhombus, an equilateral quadrilateral. Yeah, I think that's going to be true. All right, we'll work more on that in the future. Back to the assignments. Let's see, where did we leave off? We got the rhombus. All right, so the area, okay, we didn't get to that. The area of the rhombus is what part of the trapezoid, of the equilateral triangle? Anybody get that one yet? The rhombus is what part of the original equilateral triangle? Somebody chime in, please. Rhombus, equilateral triangle.
1/2.
1/2, exactly, because the rhombus is made up of two of those smaller congruent triangles. So would 2/4 be another possible answer for this one? Would that be okay? I think it would. So you call it 2/4 or 1/2. How about the rhombus compared to the trapezoid? Rhombus, trapezoid. The rhombus is what part of the trapezoid? How many pieces does the rhombus have? How many pieces does the trapezoid have?
2/3.
2/3, nailed it, yeah. It's two of those smaller equilateral triangles compared to three. So the rhombus would be 2/3 of the trapezoid. Excellent. Back to some of the definitions I had before. I mentioned with the triangles that if a figure is equilateral and equiangular, then we call it regular. So is a rhombus a regular quadrilateral? Is it also equiangular in addition to equilateral? Are all the angles of this one the same? So I'm going to attempt to draw it on here. My particular rhombus looks something like this. Roughly. And what I know when I look at this thing, I have two acute angles and the other two acute. Nope, these two angles are obtuse. Obtuse means greater than 90. So this isn't equiangular. Yeah, so it is not, a rhombus is not a regular quadrilateral. So this rhombus is only equilateral. And it is not equiangular. Equiangular. Could you have a rhombus that's also equiangular?
Would that be like a kite?
Almost. So the definition of a kite, let me write that down while you brought that up. Ooh, I keep hitting the wrong button. Cancel. Share. Okay. New page. So a kite is a quadrilateral with pairs of adjacent congruent edges. So for example, if I were to say this side and the next side coming up, these two are the same length, then the next pair of sides that are adjacent also has to be congruent, but not to these two necessarily. So if it was a rhombus, then they would be also congruent to that pair, but I could stretch it out down further like this. And as long as this length matches that length, it's a kite. Okay? So a rhombus is a special kind of kite where all the sides are congruent. So it wouldn't be a kite. And so one thing to think about, I'm gonna close the share for a sec. If you imagine that this thing was more flexible, like made out of just edges, if I could kind of push these two angles in, imagine trying to manipulate that. See, I don't have something I can demonstrate that with here. Anybody can see what I'm trying to get at here? If I made all of these angles the same, what would I have to have if the sides stayed the same length too? I'm gonna try and show this in geometry unless somebody beats me to the answer. Oops.
Would you have a square?
Yes, it turns out it would be a square. Yeah, if you take a rhombus and try and make all the angles the same, you'll end up with a square. So a square is a regular quadrilateral. So share back on, let's write that down. Or you could say it's a regular rhombus. We have multiple definitions there. All right, so I was kind of running out of room on that page. So coming down here, so a kite is a whole separate animal. It comes straight off of the quadrilateral branch of the family tree. On the other page, we branched from quadrilaterals to trapezoids. From trapezoids, we got parallelograms. Parallelogram. From a parallelogram, we got a rhombus. And from a rhombus, we can build a square. Because we could say a square is an equiangular rhombus. Another kind of parallelogram we haven't talked about yet, let's see, I'll add that in blue here, is a rectangle. And there are a lot of different ways to define a rectangle. One way to define a rectangle is a parallelogram. With 4 right angles. Since all the angles are the same, we could say a rectangle is an equiangular parallelogram. But it doesn't have to be equilateral. On the other hand, I could make a line from rectangle to square. And then I would be able to define square as an equilateral rectangle. oops. All right, so we're kind of getting through the family tree of quadrilaterals while we do this. Let's go back to the activity. All right, so let's see. We want to, with the rhombus, fold the last vertex of the original triangle to its opposite vertex. So the last vertex is one of those pointy ones. It's one of the acute as opposed to obtuse angles. And so we want to fold that last one down so it touches. My paper's kind of thick, so this is going to be a little manhandling. But with regular paper, this works out pretty nice. And so when I do that, I get that smaller equilateral triangle that we were using to compare the rhombus with the trapezoid with the big equilateral triangle. Okay. Now, here's where the cool thing comes in. Let me just double check I didn't, back to screen share. So we just left off here, what figure is formed. Then there's a whole bunch of comparisons to make related to that. But I want to jump down. I'm going to skip that for now and leave that for you guys to play with later. Open the figure back up and fold it so that the vertices of the triangle meet. Okay, so this is kind of a weird direction. So open it back up and think about that. How would you make the folds happen so that the original vertices of the triangle meet? And then what kind of shape do you get? So if you open it back up to the triangle and you just let it go for a second, and you just kind of gently push on those sides, you can see they meet, and you get this interesting three-dimensional object. So I'm going to stop my sharing here. So when I let the folds go, right, here's my triangle, they kind of want to head back in toward each other, and if I gently let those vertices touch at the top, I get this shape right here. And it goes by many names. We're going to try and
call it like a pyramid?
It is a pyramid. Okay, now it's not like the Egyptian pyramids, right? Because it's got a triangular base. The Egyptian pyramids had a square base. So this is a pyramid with a triangular base. Now, even better than that, it has an equilateral base. It has equilateral edges, so it's got some special properties related to that. The seams where the sides meet, those are called edges. And the technical name for these triangular sides, they're called faces. And remember I said slang was side, the word side was slang. And the reason is, when we're talking about polygons, a side is a straight line. But when we're talking about three-dimensional object, the side is something I could paint, right? So that's different. So technically, this kind of a side that's part of a plane is called a face. And this kind of a side that's a line is called an edge. So we have edges, faces, and vertices, the points. So this particular sucker has 1, 2, 3, 4 faces to it. And you might think it's a quad, a three-dimensional quad something or other, but it turns out it got a different name. Is it Greek maybe? For 4 is tetra. So you might have heard of tetrapods. Tetrapods are animals that walk on 4 legs. So this is a tetrahedron, and hedron refers to these faces. So it's a 4-faced object. So it's called a tetrahedron. And I expect most people didn't know that. Had anyone heard that word before, tetrahedron? Maybe not seen it, but heard it, maybe even seen it. Perhaps not in this lifetime. So question number 20 is what I jumped down to here. And when we let the vertices of the original triangle touch, we get a 4-sided figure called a tetrahedron. And on a lot of these questions, I kind of give the answer next to it. Places where I don't give the answer right away are some of the fractional answers. And we can go back and do those later. All right, surface area of the tetrahedron. What is its surface area if the surface area of the original triangle is 1? So here's my original triangle. This has a surface area of 1. And then I fold those sides so they make the tetrahedron. So the question is, if I were to paint this face of the whole triangle, the big one, is that any different than painting the tetrahedron?
No.
No. So if the area of the original triangle is 1, the surface area of the tetrahedron is also 1. So they have the same area. They match 1 to 1, which is kind of cool. All right. So I apologize, we're running a little late. We had that thing to do with Khan Academy. Can you spend about 10 or 15 minutes more with me to do the last few folds? We're almost done. Let's see, where am I? Right there. Okay, let's go for it. So I'm going to go back and show you what I'm doing. Oops, what happened there? Something weird just happened. I don't know what just happened. You guys disappeared. Oh, you moved over to this screen, I see. All right. So I'm opening back up to my original triangle, and I have the flaps. I'm going to fold toward them. So here are the flaps of the original circle. I'm going to leave it as this triangle here. And then what I want to do is I want to take one of the vertices of the triangle, and I want to fold it so it touches the center of my circle here. So it doesn't matter which one you start with. So I folded down the tip so it got to the center. And so I have this new shape here. And hopefully we all remember what this shape is called. It's a trapezoid. And we're going to continue folding. So what we're going to do is we're going to rotate it so that one of these other original vertices is on our focus. And we're going to take it and fold it down to the center. So now I have this shape right here. What is this? It ain't a trapezoid anymore, right? Over here, it was a trapezoid because I have 4 sides and I have a pair of parallel sides. But once I make that additional fold, I no longer have a trapezoid. Anybody want to give this a name?
Millennium Falcon.
Oh my gosh, it kind of is. That's cool. Huh. I wonder if the Millennium Falcon could be classified. It didn't have a round back though. It had some straight sides, but some of it was curved.
Isn't it also a diamond?
It turns out diamond is not a mathematical term, but it does look very diamond-like. I would agree with that, but I don't have a definition for diamond in my math textbook. How many sides does it have? How many edges?
5.
Yeah, so it's a 5-sided polygon. Does anybody know what we call a 5-sided polygon? Exactly, a pentagon. So like the Pentagon in Washington, D.C. So new shape, Pentagon, is a 5-edged, try to stop using slang, it's hard, polygon. Now this particular 5-edged polygon has no, it doesn't have any, all of the angles aren't congruent, all of the sides aren't congruent, so it's not regular, it's not equilateral, it's not equiangular. I mean, it does have some symmetry to it. I could draw a line from this point here through the middle of that opposite edge, and I could fold it in half and get a mirror line of symmetry, but that's about it. It's got one line of symmetry. One more step, sort of, we're going to take this last vertex of the original big triangle and we're going to fold it down to the center again. And this figure here has a lot of cool properties. And let's see, there we go. So, does anybody want to tell me something about this particular figure?
It's called a hexagon.
It is a hexagon because of its 6 edges or 6 angles, whichever way you go. Okay, so let's make a note of that. Share, share. So hexagon, hexa, 6, gon, angles. Well, I'm going to use edges, 6 edged polygon. Now this one is actually a very special hexagon. Can anybody tell me what properties it has that might make it specialer than others? What is special about this one?
Is it parallel?
Well, it turns out opposite edges are parallel as we go around. That's kind of cool. And let's see, can any old hexagon have opposite edges parallel? I think, I don't know if this is true off the top of my head. If all of the angles are congruent, that will lead to parallel edges, pairs of opposite parallel edges in a hexagon, but not necessarily sides. Do you think the sides of this thing are congruent? Did we make all of the folds exactly the same way?
Yes.
Yeah, so it turns out this is equilateral and equiangular. So what's another name for it if it's equilateral and equiangular?
Regular.
Yeah, it's a regular. So in this case, we have a regular hexagon. Because it is both equilateral and equiangular. All right, so I've gotten through most of what I wanted to get through with this activity, which also kind of finishes off what was in section 10.1. 10.1 was about what's a point, what's a line, what's a plane, what are the different kinds of lines, like line segments or rays or just regular lines, and then different kinds of angles. You get to watch the video, read the book, and try the homework. Now we've just classified some polygons, and we'll spend more time on this in the next section. There's a bunch of other questions here relating to areas, and so I'm going to stop here and leave that part for homework. But I think what we should do is if anybody gets stuck on any one of these, then post it to the next assignment, which is the learning forum, and say, hey, this is what I thought the ratio was of those two things. Can somebody help me verify that? Some things that helped me figure this out was drawing on it. So I'm just going to open my screen up and show you what I mean by that. So right now, I've created 3 different equilateral triangles. I have the big equilateral triangle I got from the circle. And then from folding the circle into the first trapezoid and rhombus, I got a medium-sized equilateral triangle. Then we did our second rounds of folds where I took the vertex of the triangle and folded it to the center of the circle, and that gave me a third smaller equilateral triangle. So altogether I have 1, 2, 3 different sizes of equilateral triangles here. And the hexagon is made up of 6 of the smallest equilateral triangles, right? Can you see them there? All 6 of them living there. And if I unwrap that, that 6 turns into 7, 8, 9 of those little ones. So the big triangle is made up of 9 of those little triangles. The hexagon is made up of 3 of them. Where we're going to run into a little difficulty in making comparisons is when we try to do things like compare the rhombus to the hexagon, because the rhombus is made of those medium-sized triangles, and they do not match easily with the smaller equilateral triangles that made the hexagon. And so this is where I would recommend you start with your pencil, tracing some of the fold lines we made for the rhombus, and for the hexagon. And then a solution kind of pops out from there. But it requires a little bit of play. So what I'd like to have happen from here is try to do those Khan Academy exercises. The videos in Khan Academy are optional but recommended. I'm going to share my screen again. Share. We've answered about half of the questions on this activity. And then any question you get stuck on, and the harder ones are these fractional ones, post, if you don't feel like posting to the forum, I wish you would post to the learning forum, take a risk. There's tons of stuff all of us don't know, so don't worry about it. But if you don't feel comfortable posting to the forum, then just message me personally, and I'll write back to you, and I'll probably anonymously post for you in the forum. And then if one of you doesn't reply to somebody else's question within a day, then I'll jump into the forum and start answering questions if people get stuck on any of these. So this is a 10-point assignment. You guys have already done more than half of it. If you answer like 90% of these questions here, I'm gonna call it a 10-point assignment. And if you only get stuck on a few of these, no big whoop. But give it your best try on each of these. And it's the last ones that are the hardest ones, because that's where I ask you to compare the two different kinds of little triangles, the medium-sized one and the little one. One last thing, stop sharing for a second. And I don't know if anyone read further in the directions and tried this, but check this out. So now when I open it up into the original triangle, it's got two sets of folds happening. So what I'm gonna do is kind of gently make this into a special shape. So I'm gonna let both folds happen. And when I do that, is there too much light here? Can you guys see that okay? My contrast kind of sucks on this end. Should I turn down my lighting? Can you kind of see what I got going on there? They kind of want to fold down together to get this new weird 3D shape. And it turns out this new 3D shape is a lot like the other 3D shape we had. This one right here, the tetrahedron, but with the top chopped off. So this actually has a technical name. It is called a truncated tetrahedron. And there's a couple of questions in there about the truncated tetrahedron compared to some of the other shapes. Like, what if you were to paint the truncated tetrahedron? What would its area relate to, say, the original triangle or the hexagon, maybe? All right, does anybody have any questions for me before we part?
For Khan Academy, does it let you do like a late pass?
I do not know the answer to that. So let me figure that out. Let me see if anyone else has tried to join since we started. Refresh. Doesn't seem so. Oh, something's happened. Okay, no new students. All right, so how does time work with Khan Academy? Let's see, I have an assigned screen here. That's different. Does that show what I've assigned? Some of their tools I haven't quite figured out yet. Manage actions. Edit, what does that do? That lets me change the date. Okay, so my guess is I can't assign late passes, but I can probably go in and change dates if I need to. And then what happens if you do something after the date? I'm gonna make a note to explore that. Will it be nice like my open math or a pain in the butt like that thing we had in the fall? So I'm going to check that out and get back to you. Khan Academy. Late work. All right, I'll look that up. And if, yeah, I'll look it up and get back to you. And if I think it's going to be a problem, I'll just extend the dates by Saturday if necessary. So do your best to get these done. Again, in your view, where did the student view go? The arrow on the side indicates it's a video, and those are optional. And then the things for points that I'm looking for, the things with stars on them. And there are, if I remember right, 9 or 11 stars. I think there were 11. I think there were 9 what they called exercises, and they had either 4 or 7 questions each. And then there were 2 quizzes, which had 5 questions each. All right, we'll check that out. Other questions? Okay, so I guess that's it for now. If you get stuck on something, be sure to message me, or if it's one of those questions about the activity, you can message the group through that learning forum. And those are the assignments for this week. There's not going to be a share your work assignment. And then I posted, I don't know if you all saw the post on that in announcements, the password for the take-home midterm test.
And we're okay to use out like the computer and all that?
Yeah, you can use some. The only thing there is I just ask that you not consult another human. If you want to ask a classmate about something, pick a similar homework problem and say, how did you do this in the homework? And I'll just bring this test up for everyone to see here. Let's see, to get there, I guess I can go to assignments. So just copy that password, go find the midterm. Where'd you go? Midterm. And you can enter the password anytime. It's not timed, so you can jump in and out of it as you please. Google's trying to remember the password for me. No, thank you, I don't need it. So there's just one question with a whole bunch of parts. So everyone's gonna have the same kind of data. It came from a study done at the University of Puget Sound, where we have the GPA of a bunch of their students. And I have, all of this is really the same data. So the first table here is the males and the females all mixed together. And there's 50 of them. And you each get a random sample of 50. So you all have slightly different samples. And some of you maybe have more females than males, some will have more males than females, it depends. So the sample I got in this column over here, there happened to be 21 females. So I just pulled it out and listed them separately. So really all you need is this table here on the left to do this. But if you decide you want the males separated from the females and you don't know how to do that in a spreadsheet, I listed them here too. So all of these numbers and these other 2 tables are here. They're just shown differently. So that's the data. And then I just want a bunch of statistics. So from all 50 students, I was just messing around here. From all 50 students, how many were there? What's the average? What's the standard deviation? I link out here to a thing called the coefficient of variation. So check that out. That's a new thing I'm having you try. And then the 5-number summary and the IQR. Then I ask you to apply the IQR rule like we did a couple of weeks ago. And then the 2 standard deviation rule like we did last week. And then some of these questions are related to percentiles, which is like that normal distribution that we talked about last week also. There are no direct questions about the normal distribution here, so this is mostly from weeks 1 and 2, and only a tiny bit from week 3, and nothing from this week. And then I ask you to give me some statistics on the males versus the females, and then I want you to write up a paragraph thinking about some of the things I mentioned here that compare the male to the female data. Like on average, the males have a better GPA than the females, or the females have a higher GPA than the males? How did you determine that? who has more of a spread. So just kind of think about it. Also, I wanted you to make, when you're thinking about it in this summary, make a couple of histograms and a couple of box plots. So if you like stat key for box plots, you could just highlight the female data and bring that into stat key and make a box plot. Then you could bring the male data into stat key and make a box plot if you want. So you could do it in a spreadsheet, or you could do it in stat key. Stat key gives most of these summary statistics, but not all of them. Actually, stat key does everything you need with just a couple of other pieces of arithmetic. So you all have the same assignment, you just have different numbers to work with, but it's all about GPA from Puget Sound students, male versus female. And then you can upload work into this box here by either using the attach button if you have like an Excel spreadsheet, or you could use the link button if you have a Google shared spreadsheet. And if you get stuck on anything here, just message me and I'll help you out with the test as best I can without giving you the answers. All right, I guess that's it now. Thanks for hanging out with me today. I hope you're all well. Have a great day. And I keep getting signed out. That is the weirdest thing.